Compound 1 has been prepared and studied to investigate a novel type of intramolecular elimination mechanism. The proposed mechanistic pathway for this transformation is presented below. Complete the mechanism by drawing curved arrows consistent with the change in bonding in each step. So we just have to draw the arrows, but I'll also annotate with the identification of each mechanism. So always you have to compare the reactant and the product, or at least the intermediate here. I see all our chirality is preserved, and the right side of the structure is pretty much retained, except the left side. You see that carbon-oxygen double bond is no longer double bond, and also we have a base as our reagent. And looking at the structure, somehow we introduced more oxygen here. So considering from this, there's no change on the, but on the left side we have some change, and we still have 2 carbon, but we now have 2 oxygen in the intermediate you see here. So that means there's a high chance that the lone pair from the hydroxide is going to attack. In other words, we need to put this or add it to our structure, and to do that we have to do the nucleophilic attack. To that carbon there, the carbon that's attached to the double bond with oxygen. And by doing that, the carbon cannot have 5 electron pairs around. Then we need to have a concerted process of that pi bond need to be pushed toward the oxygen here. Okay, that way we're gonna have the minus charge located on that oxygen, and then we're attaching that OH minus to our structure, and there we have it. Now from here to down here, okay, we have to see what's the difference. Now the right side structure is definitely changed, but up to here, so on that right is preserved. Okay, so we do not want to really touch that, so we just have to play with this side and then probably break that as well. Actually, we have 3 broken parts. Yeah, we have 3 broken parts. So how does this work? Well, we're gonna have a funny thing going on, because not only proton transfer happen, but also there will be a leaving group. So anytime you see the minus charge and we don't see the minus charge there gotta be some kind of proton transfer or nucleophilic attack. So I'm gonna draw the lone pair around that, the negative charged oxygen, and then he's gonna grab that hydrogen. That's because over here we have to create a double bond. Once he grabs it, the hydrogen, now the bond, the electron located between the hydrogen and the carbon is gonna play a key role in making that double bond over there. Okay, let me draw it bigger. Okay, but then we cannot have 5 pairs around the carbon, and also on the next structure we see the broken parts, right? So we're gonna break the bond, that wedged bond between the oxygen and the carbon, and then I'm gonna make it simple by placing it on the single bond between the carbon and the oxygen, so that we get that double bond. Okay, so that in a way acts as a leaving group. And this is like a proton transfer. And also this was the proton transfer. Okay, and by the way, this was just to show you that we are not touching the right side structure. So there we have. And then, let's see, we have to compare this structure with that structure. Oh, there's one thing I forgot before we go there. You see that hydroxide is cleaved up, right? And also the carbon cannot have the 5 pairs around, and I just forgot to place that. So now we have the 3 molecule instead of 2. So we have a 2 living structure, or 2 living groups. Okay, so here we have, and now to compare this with this, our final product, the big structure is reserved. Okay, so I will draw that water as this, or you know what, you could just put the lone pair around that oxygen. Oh, over here, by the way, right, like that. And then I don't see the hydrogen on that, that oxygen. So he's gonna grab that hydrogen, we call that proton transfer, and then that bond is now gonna locate on the oxygen to create a negative formal charge. So this is gonna be proton transfer.